Okay, so I'll talk a little bit about the evolution algorithm. This some people here will care about because you complained to me about various numerics, so that's what's in here. So the time in binary C, I mentioned this earlier, the time is stored in mega years. It's in the variable model.time, which you can find in Stardata. That's quite easy. So at each time step, what we do is we update the stellar structure, we calculate derivatives, we apply those derivatives, and then we flush what's called the event queue at the end. So I'll talk to you what these are. We then check for a rejected system. This is when things go wrong. And we do something called evolution splitting, which is handy for people doing supernovae. So again, here's the cut down code for what evolved system binary C does. This is essentially the evolution step in the binary C algorithm. Until recently, we used to have two algorithms for evolving. One was the BSE one, which was based on the legacy BSE code, and binary C. In the latest version, we only had binary C, because the BSE one I refuse to maintain anymore because it's crap. So it's crap. It works fine for certain things, but for certain things it breaks. So the new one is much more flexible and more simply coded. So it's good. So what we do is, this is a loop that essentially, as long as the evolving variable is true, means we are evolving the system, we loop over this thing. We update the model number each time. We have a check at the top, which can return evolution break. Essentially, that's checking to see whether the maximum time has been gone past, or if both stars have zero mass, then we just stop, because obviously nothing can happen, things like that. So it's relatively straightforward. So you've got to stop a check at the top. Otherwise, we initialize the system every time step. That sets a few things up that you need every time step. We call the evolution function, which returns a status here, and we check the reject flags. There are 3 flags that can be set in either of the stars, and we'll talk about this in a second, which can then reject that time step. If the reject is false, which means everything worked, we call the success function. That sets a few things when everything works. We then check for Roche-Loeb overflow. Now, Roche-Loeb overflow returns an integer that can either be that we have started Roche-Loeb overflow, or we're in Roche-Loeb overflow, or Roche-Loeb overflow after spiraling. Now, what that is, it means that for every time step, you can calculate the rate at which the system is losing angular momentum. So, for example, imagine you've got 2 black holes spiraling very close to each other. Then what you can do is you can detect whether they would merge in that time step or not. In theory, in order to actually resolve that spiraling, you need very, very short time steps. You can imagine, you know, like you see in these black hole merger waveforms. I mean, there's no way we're going to try to resolve that. So what we do instead is we calculate the time scale in which it's going to merge, and if it's shorter than the time step, we say it's going to merge. And we just pretend it merges there. That should be accurate enough. If you're after more accurate time, you're using the wrong code. Okay? Go and talk to Alessia over there about more accurate models. This is what she does. But it's fine, I think, for most of what we do. So we then test whether the system is a contact system, in which case we call the contact system function, which merges things, or, well, it sets an event which merges things. Otherwise, we start the Roche-Loeb overflow. Otherwise, if there is no Roche-Loeb overflow, we just set that flag to false. Then we check the evolutionary status. If it's stopped, that means that things are finished, then we finish everything. If the reject is true, on the other hand, we call evolution rejected. Now, what that does, we'll describe in a little bit, but it essentially takes the time step back and repeats it with half the time step. So. Now, things have worked, so we then look at events, and if there are any events, now events are things we define as instantaneous things. If there are any events, we catch them, we do what we're supposed to do. We'll define that in a second. We then look to see whether the evolution needs splitting, and I'll talk about that in a second as well. If that isn't the case, we do logging. That calls the log function, log every time step. We increment things called fixed time steps. These are time stepping where I decide to fix where the time steps are, like every mega year. You can do that. There's an algorithm for doing that. It's in the cookbook. It's got examples for how to do it. So if you want to output every 1 million years, it's very easy to do. Or you can even do it in log as well. So it's simple enough. We set the next time step, and if we are still evolving, we save the current star data to the previous star data. Now that's very useful. That means that at every time step, we have a previous star data. So you can calculate numerical derivatives, you can see what happened last time and compare it to this time. There's a function called the evolution diff log, which does a difference between the current star data and the previous one. And if things have changed, it outputs to a log file. So things like that. So it's quite smart in that regard. Now, how does the evolution work? Now, in the evolution step functions, we have three schemes. We have a forward Euler. Right? So for those of you who know about differential equations, which hopefully is all of you, the forward Euler scheme is the simplest. It's also the quickest. It's also the least accurate. Right? So you choose. We have an RK2 and an RK4 as well. The RK2 is 2 steps, the RK4 is 4 steps. Again, it's a lot more work to do an RK4, but it is more accurate. In most cases, it'll make absolutely no difference whatsoever. If you have a wide system, it'll make no difference. If you have a closed system with a lot of mass transfer, and especially tides, it can matter which one you choose. That's because the tides equations are very stiff. They've got factors of R over A to the 6, R over A to the 8. Those are quite stiff. So that makes a big difference. There's not an implicit scheme in here yet. I would love anyone to write one for me. That would be good. There's a predictor corrector scheme that I did try to put in. I'm not sure it works at the moment. It did for a while, but that in theory could be a step forward on this as well. But again, it's more, it's a question really of do you need it? If you don't need it, there's no point putting it. So. Now we have functions which calculate the derivatives, like these three here. The mass and angular momentum changes, that's just calculating dm dt, dj dt for each of the objects. Also stellar evolution and binary star evolution. Binary star evolution calculates for the orbit, for example, stuff like that. So if you're going to do anything that requires changes of things, you need to define a variable there's a binary C derivatives.h file, which I haven't talked about too much. You can define your own derivatives, and it will automatically then update those for you. Each of them has there's an applied derivatives function which you can use to do that. The derivatives are stored in these arrays, so the model derivative is for things like orbits and stuff like that, and the star derivatives are things that change each star. It's very simple. Time steps can be rejected. This tends to happen if something isn't resolved. So for example, if you try to change something too quickly, then it will reject the time step and try again with a shorter time step. In this case, it will be whatever this macro is set to times the previous time step. And that works very well, actually, at the moment. It seems to work pretty well. It's kind of like the way a normal stellar structure code would work. Now, the time stepping itself, we've done a lot of work on time stepping this year. It's a little complicated for time stepping because there are lots of options. And they are all, typically time steps are, you either set dt or dtm. These are the same, it's just dtm is 10 to the minus 6 times dt. Okay, because one's in mega years and one's not. And this is really a step back to the old BSE code that I haven't actually eliminated yet. I probably should at some point. But it doesn't really matter for what we're doing. These are all set in the stellar time step function, which has lots of sub-functions that are called. Each phase of evolution has a different function that gets called. Plus, there are other things like angular momentum loss or winds or something like that. You want to resolve all of these. But most of the time steps are set from a formula like this. So you take whatever the variable is, divide by its own derivative, and then multiply by a number less than 1. And that gives you a rough idea. So the time scale of what you're doing is this fraction here. But of course, you want to resolve the time scale, so you divide it into smaller chunks. Now, these F, which are the time step multipliers array, there's a whole array of these, which are all set in the code. You can set them as command line arguments if you want as well. Very easy. And so you can actually decide how much you want to resolve each time step. And if you set F to 0, that time step is ignored. Okay? There's something like 50-something different processes at the moment which can be set. The defaults are all set in this function, time step set default multipliers. And as I said, you do it on the command line, and it's very easy. They each have their own macro as well, so you don't have to remember the numbers for each. So you also have maximum and minimum time steps. This one's not quite right. This should say maximum nuclear burning time step. Sorry, I missed a couple of words out there. The difference between the maximum time step and maximum nuclear burning time step is that maximum time step applies for all stellar types. Maximum nuclear burning is only if you actually have nuclear burning. So white dwarfs, black holes, neutron stars are ignored in that case. So you can have longer time steps for that. And that's very useful if you don't really care about white dwarfs. So, of course, it's up to you. The minimum time step is usually 1 year, which is 10 to the minus 6 mega years. And there's also something called the time step modulator. This multiplies the time step. And of course, that's useful because you can divide the time step by 10. If you set that to 0.1, it will take 10 times longer to run, which is bad, but you should get the same result. If you don't get the same result, things are going wrong. So it's a good way to test. A little brute force, but still handy. Now the events. Now, we had a problem this year because we were really working on putting these different solvers in. The problem is you have things which act on an instantaneous timescale. And if you're doing something with a solver like RK4, it assumes the derivatives are smooth. Of course, if you have a supernova going off, the derivatives are no longer smooth. Things just jump from one system to another. So what we now do is we put these into what's called an event. So you trigger the event in the code. So for example, here I'm setting up a new supernova event. These each have their own structure, which stores information about that supernova, the type, the mass, the exploding, which star explodes, and so on. You can define a structure for whatever you want for your event. And you call a function, well, a function macro called add new event. Then it has an event thing here defined, which is event supernova. You then define two functions. One is called the event handler, one's called the erase event handler. The event handler is what's called at the end of the time step. So you've done all of your RK4 stuff, your solver, and then you call the event. That way you don't mix your sudden change because of the supernova with your nice smooth evolution before. And you rely on your time step to be short enough that you don't really have any problems with your event going off in the middle of the time step. So you can always, if that's not enough, you can always reject the time step and make sure it's shorter. So that's where it goes through, and you have to check that it's not denied. There are cases where it might be denied if, say, something else has gone wrong with the code and then you reject it anyway. Very rare that that happens. Your event handler function does all the physics that should happen, but assuming that it happens instantaneously. Okay. So your supernova event handler, you can get the event stuff from the event P pointer if you want. Star data is passed in, and you just do whatever physics you need to do. It calls the supernova function in this case. It could be anything. Now, the events at the moment are set up to do several things. The supernovae, stellar mergers, common envelope evolution, and I think novae as well. I'm not sure, probably novae as well. So the reason that these things are done as events is because they're always treated as instantaneous. Now, in the old BSE code, these would be done just on the fly, and because there's no real control over the time steps in the same way that we have. So it's a lot less systematic than the way we do. But hopefully this should work very well. If you have any problems with this, let me know, because it's still quite new code, but it seems to work for what we're doing. And finally, I think the evolution splitting. How does evolution splitting work? Well, a normal evolution, you start at time 0 and you move to the right here to the end. Everything has a probability of 1. Okay, now, the reason I say probability, what does that mean? In the binary grid, when you run lots of stars, not all stars have the same weighting. So low mass stars are much more likely than high mass stars, so different probabilities. But if you're running one star, you've got a probability of 1, so that's easy, it's fine. But what you might want to do is you might say, okay, what happens when my star has a supernova? Well, remember, when you have a supernova, you have Monte Carlo kicks, so the kicks are in random directions. So you might want to say sample that directional kick, rather than just do it once. And so you can split the evolution at that point, and it will restart at the supernova each time. But each of these reruns, which has a random kick to it, then has, let's say there's 4 of them, then each of them has a probability of a quarter. Okay, so you've still got the same number of stars up to that point. And you can turn the splitting to be true from the preferences option. There's a couple of other options. There's evolution splitting n, which is the maximum number of splits, which here is 4. And then there's also the max depth. That means how many times you can branch the evolution off. So you could have a binary that has 2 supernovae, for example. So if each of these sub-branches has a supernova, then you might or you might not want to split doubly. I mean, it's up to you. And that's what the max depth does. So that's the evolution algorithm in a nutshell. It's a lot better than it used to be, I have to say. In the old days, it was only forward Euler. There was no splitting. There were none of these nice features, no events, nothing. It's turned into a much more professional code now, I think, than it was before. And a lot of this has been in response to challenges that some people here have sent me. So please do keep those coming, because it certainly improves the code. So any questions on this before we go on?
in binary C, is the maximum number of splits you can have at the moment 2? Just one for each supernova, or is there anything else?
Well, yes, it's de facto 2 because you can only have 2 supernovae. But there's no reason why you couldn't split at any event that you define. At the moment, I've only coded it to work for supernovae, but you could put in a split on anything. So you could split at a certain change in stellar type or something, or whatever you like. So yeah, in theory. I've never tried that, but it should work.
Are there any other random processes that might require splitting?
No.
Okay.
At the moment, the only Monte Carlo thing is the supernova case. So at the moment there isn't, but that doesn't mean you might not think of something. Sure. That's why I try to keep it as general as possible. Anything from the audience out there? They're all very quiet.
I'll ask them. Rob, it's Jonathan here. Do you have any error control on the time evolution?
Yes.
Like on the RK4 integration, for example?
Yes. So if certain variables change by too much, you can just reject the time step.
And make it smaller?
Yeah.
Okay.
Yeah, that's very easy to do. In fact, it does. At the moment, I think if the angular momentum changes by more than 1 or 2% or something, it just automatically does that. There's a few others as well that will be like that.
Radius expansion, I think.
Yeah, it could be radius expansion, something like I can't remember exactly. That's actually very useful. I was recently making a Hertzsprung-Russell diagram for the Gaia group in Cambridge. And in order to resolve position on the Hertzsprung-Russell diagram, what I did was I compared the temperature and luminosity to the previous time step in the previous star data, temperature and luminosity. And if they were greater than a certain amount, I reject the time step, go back and do it again with a half time step. And that way you can always guarantee that you resolve your stream across the Hertzsprung-Russell diagram, your track across the Hertzsprung-Russell diagram to whatever resolution you want. Turned out that was very, very simple to do with the time step rejection. The time step rejection is also clever in the sense that it checks whether it can reject. So if you had an event that went off on the previous time step, it won't allow you to reject it. And the reason for that is events are sudden changes in these tracks on the Hertzsprung-Russell diagram. So you couldn't possibly resolve that even if you wanted to, because it's in 0 time. So it's not stupid. It does do that in the way you would expect. Anyone else?
What kind of time step does it take after an event?
I think it has a very short time step after an event, and it ramps it up after that. So it starts at the minimum time step and then ramps up. So the idea being that you do resolve whatever comes afterwards. That's exactly what it does at the beginning as well. So the first 10 time steps are all at the minimum time step. It's called the burn-in at the beginning, and then it starts accelerating after that. That may seem like a little bit of overkill, but sometimes you need that. And if you have a very close binary, you probably do. So for example, if you start 2 very massive main sequence stars very close, the tidal timescale is very short. So you do actually need to have very short time steps, but it can't possibly know that because you don't have any previous evolution. So that's why you start with a very short time step at the beginning.
Is that only when you initialize the binary, or is that on calls to evolve binaries?
That's when you initialize it. You can always reset the model number and then it will do it again. It will be very slow.